just like the intro, chapter 5 intro. So we're on this chapter called Root Locus Analysis, and I'm following the Nice textbook in having a chapter on root locus analysis and then a chapter on root locus design. The root locus analysis chapter is giving us the tools to analyze and define what a root locus is. And then in the next chapter on design, we'll use that as a design tool. Those will be the only controller design method that we'll learn is root locus, but it's very powerful. You can design virtually all of the single input, single output control systems that you would ever want with this method. So it's very practical for most people. Even if you don't end up being a controls engineer, this is the type of thing you might need to be able to do with controls, even if you're not a controls engineer. But it's also a segue into more in-depth controls work. So yeah, root locus. So just to give you a preview, it's a graphical technique for designing for closed-loop transient response from open-loop knowledge and some cleverness. So this technique was invented in the 1950 approximately. I think it's a paper that came out by Evans, and it was a different sort of controller design technique, analysis technique. We actually won't learn the earlier version in this course, but if you go on to a more advanced course in controls, including my robotics course, we go through it. They're so-called frequency domain design techniques that are equivalent in a lot of ways to root locus, but I think root locus is more intuitive, so we're going to focus on that. So a system's transient response is dominated by its poles, right? So we've seen that a lot. Transient response is dominated by poles. Of course, stability also is dominated by the poles. And to some extent, the steady state error, I mean, and you think of it as, are there any poles with the origin? Are there any integrators in the system? Pretty much the poles dominate. Transient response, definitely. Of course, also along the way, they dominate the other performance characteristics, the stability and the steady state error concerns that we have. So the poles are what we care about. The closed loop poles are what we care about most, right? That's the poles once we put feedback in. That's what we care about the most. So a system's transient response is dominated by its poles. For a system with feedback, solving for these closed loop poles is challenging, as we'll see in lecture 5.1. So on Wednesday, I'll go through an argument for why it's a challenge to actually determine where these poles are when you're designing a system. Okay. So due to the use of complex analysis in this chapter, it is recommended that the reader review lecture A1 before proceeding. So that's what we're going to go through today. It's just a little bit of math background so that we're prepared to do the rest of this chapter. Now, but I don't want us to lose sight of this, though. This is what we're going to come back to, that solving for these closed-loop poles is challenging. And the root locus technique, using some complex analysis that we'll fill in this lecture, is going to give us a way to do that, or a technique for using some clever ideas to predict where those closed loop poles will be, even though we won't solve for them in closed form necessarily. So, yeah, it's gonna be fun. Lots of good stuff. Okay, so we'll get back to this, but for now we're going to do some math. So we need to do some complex analysis, and so this is lecture A1, complex functions. There's a little bit in this lecture that we won't cover, and if you stuck around and did some more advanced controls courses, then you would need the other parts. But for this class, we only need a subset of this complex functions lecture. But I'll kind of guide us through it. But there are some really important aspects of it, so I'll really highlight those. So a complex function, f, maps a subset of the complex plane to the complex plane. So in other words, f is a map in this mathematical notation. F is a map from the complex numbers to the complex numbers, or a subset of each, right? For instance, a complex function f can map a single complex number, s0, to another, s1. If you pop it into the complex function, so plop s0 into a complex function f, it'll return to you a complex value, which is the so-called image of the function. So we've got this understanding. I think that, so I actually think in calculus, you guys don't really do a lot of complex stuff. It's mostly real functions, right? I don't know if you guys do. Do you guys do a little bit of complex functions? Or is that not really? No. So complex functions are a little uncomfortable, but we've actually been using them all this time because transfer functions are complex functions. So we kind of have the idea of a complex function. If you put in a real number into a real function, you get a real number out, right? Complex function, if you put a complex number into a complex function, you get a complex number out. So you've sort of seen it, it's been around, but we haven't talked about it explicitly. So we're going to talk about it in a pretty mathematical way in this lecture, but it's not something that's totally unfamiliar to you. So a curve, this is a definition, in the complex plane is defined as a continuous function mapping a closed interval of the reals to the complex plane. So let's parse that again. So a curve is defined as a continuous function mapping a closed interval of the reals to the complex plane. So you take something on the real number line and you map it to the complex plane. Okay? A contour, and this is going to be our focus, a contour is defined as a directed curve consisting of a finite set of directed smooth curves, the final endpoint of which is identical to the starting point. So I know that's a little bit hard to parse, but this is a nice representation of it. So on the real line, we have some interval from A to B, and it's closed. Is anybody taking, any math minors in here? Anybody taking real analysis?
People have been telling me not to take it.
Oh, so fun. So fun. Anyways, this is the difference between a closed set and an open set. The endpoints are in it, or the edges are in it. So you know how you have an interval with the endpoints or not with the endpoints? A closed one has the endpoints included, an open one does not. I know.
I think the class is not bad, but the teacher that teaches it makes it pretty complex.
We don't want to hate on YouTube. We don't want to do hating of professors on YouTube. We stay away from that completely, whether it be me or others. So remember, this is recorded. I want to talk ill of dear professors. We love you all. Okay, so this is an interval here, especially if you have tenure and I don't. This is an interval here on the reals. And we want to take this interval, we want to map it to the complex numbers. And this is really, it's just kind of fun. It's geometric, right? So you got this interval. We're going to map it to a contour on the complex plane. So this interval for some point in it, if you chose this point in it, it would map to, say, I don't know, this point here on the complex plane. So defining what that map is, so I called it gamma here, defining what that map is defining the contour, okay? All right, so that's a contour. You guys have seen parametric definitions of things before, right? Like parametric plots, cardioids and ish. You guys did that. That was like pre-calc or something, right? I don't know. It's really been a long time, guys. So I'm like really honestly asking. Is that when you guys learn how to do parametric plots? Like, it's like when you guys are like cosine t comma sine t, and these are like x and y coordinates. Oh, yeah, you guys remember that? Yeah. So that's essentially what we're doing, but we're doing instead of x, y, it's complex. T would be the real number that we're plugging in. Yeah, I know. So anyways, you come to more advanced control stuff, we get to draw cool cardioid stuff again. We're not really going to get too in-depth into contours in this class, but we get to like see them and see that this is what we could play with if we did more controls. It's a teaser trailer is what we're doing. So, good, contours. So a contour can be mapped by a complex function. And this is our primary concern when we get to more advanced control techniques, is mapping contours. The image of a contour, gamma, mapped by a complex function f, is itself a contour as shown in figure A2. So, not only can you take a real interval and make it a contour, you can take a contour and map it via a complex function to another contour. I know. It's crazy. It's crazy. You guys didn't even know how much fun you were going to have today when you came to class. You're like, not prepared. It's Monday, still having this much fun. Okay, complex functions are of interest in control theory because transfer functions, one of the central mathematical objects of control theory, are complex functions. The utility of evaluating and mapping contours with complex functions arises especially in root locus design, which is what we're going to do, and frequency response design, especially the Nyquist stability criterion, which we won't do in this class. Aw, was the response I was expecting. Okay. Example A1. So this is just a simple example. Let's just get used to mapping a single point with a transfer function. So, map the complex point S equals a complex number 1 plus J3 with the transfer function, which is a complex function, right? H of S. So H of S takes in a complex value S and it gives you back a complex value. So it's a complex function. Sometimes we say that we are evaluating the transfer function at the point S equals 1 plus J3. There's a very mathematical term would be to map a point using the complex function. However, the less mathematical way to say it would be to evaluate the function, right? We talk about that a lot, evaluating a function at a point. So that's another way to put it. So I think we can all do this. I'm gonna give you guys a few seconds to try to do it on your own, and then we'll do it together. Okay, so let's bring it together then and see if we can evaluate it. So it's a one-liner here, but it's going to be, along the line. So h of 1 plus j3, just like any function, we just plug in the argument wherever the argument variable shows up. So s becomes 1 plus j3, and then we have the plus 4 still. In the denominator, we have 1 plus j3 again, s, minus 1. 1 minus 1 for the reals gives you no real part remaining. In the numerator, you can combine the real components. So you have 5 plus j3 in the numerator. In the denominator, we just have j3 left. Can you cancel the j3s? No. Well, I mean, no. You wouldn't want to. So what do we do? We typically try to rationalize these things, right? So-called rationalize them. So we want to write them as a single real and a single imaginary component. So we want to bring this numerator j up. And we typically do that by multiplying the numerator and denominator by the complex conjugate of the denominator, right? That always works. When you just have an imaginary part, you can just multiply by j over j, right? Because j times j is what? -1. So we do j over j times 5 plus j3 over j3. J times j is -1, so we have -3 in the denominator. We have the real part in the numerator is going to be j times j, which is -1, times 3 is -3, divided by -3, which is what? 1. I know. So then we've got, in the other term is j times 5, so that's the imaginary part. We're still going to have it divided by this -3, right? So negative j 5 over 3. And that's going to be our rationalized version of that. So not too bad. I mean, I think we all could have done that before this lecture. But just trying to convince you that, yes, the transfer function is a complex function. Okay, so a geometric interpretation of complex functions. And this is kind of the big payoff for us in this class. This is what we're after. So it is often helpful to interpret the complex mapping of a point or a contour geometrically. Let us consider a transfer function h of s with complex zeros zi, complex poles pj, and real scaling factor k. Of course, these zeros and poles, remember the reals are just a subset of the complex numbers, right? So when I say complex, they might have zero imaginary part. They could just be reals. So all of the poles and zeros we've ever considered would be complex, right? Because reals are just a subset of the complexes. Okay, consider each factored term of the transfer function in terms of its magnitude and phase. So this is something that we've done previously when we talked about Bode plots, right? We took that transfer function, we were thinking about it in terms of magnitude and phase, right? So this is related to that. So we can write the magnitude and phase of the transfer function as follows. So, and we've done something very similar to this before with Bode plots, but we're just reminding ourselves that we can do this. So the magnitude of h is, there are some scaling factor times the product of the magnitude of s minus all the zeros divided by the product of the magnitude of s minus the poles. Okay? So this is a mathematical statement that's true. The magnitude can be written like this. And we're going to take a geometric interpretation of this in just a moment. But let's also do the phase before we do that. So the phase of h of s is equal to the sum over I won't do a top one. So sum of over all of the i's of the angle of s minus zi, so the s minus the zeros, minus the sum over j of the angles of s minus pj, which is where Wycliffe was born. That might have been too obscure of a reference. Wycliffe Jean, you guys know this guy? It's pretty legit. He has a song, PJs. I was born in the PJs projects. You guys know this? Okay. Anyways, look it up. Look it up, kids. It's good. Okay. So this is how we can write the magnitude and phase. Sorry. It's actually legitimately a really good song. And I really like Wycliffe Jean. Whenever I write PJ, I think of PJ. Yeah, okay. So, I was not. I can't claim to have been born in the PJs like Wycliffe, but he was. So, this is a convenient way to write the magnitude and phase of the transfer function. We've done it before, actually. With our Bode plots, the only next step that we did was we took the log of this magnitude thing, right? We took the log of it so we would have sums. We have products still in this term. But that's, yeah, so this is just another way of representing that. So, we're not going to do Bode plots, though. We do something else with this. We can interpret this geometrically as follows. Let us consider the evaluation of equation A1, so that's what this boxed equation is, at a specific complex value psi. So we're going to set s equal to psi, and we're going to evaluate it. The difference is psi minus zi and psi minus pi, so they show up everywhere. If you plug in s equals psi, then we get psi minus zi, psi minus pi showing up all over the place, right? Can be thought of as vectors in the complex plane with vector subtraction as the idea. So with tails at zi and pi and heads at psi. So figure A3 shows a specific example with some specific pole locations chosen and a pole and zero locations, and then psi being the value of s that we're evaluating this complex function at. So we will go through and essentially, we're not even going to do this last example or look at the mathematical code because that's specifically talking about contours. But this geometric interpretation of evaluating a function and thinking of it as being these vectors in the complex plane, this is really useful for root locus analysis. So that's what we're doing this for. So let's unpack this. Let's just do this example kind of like in line here. The claim is that we can evaluate the magnitude and phase of this transfer function by looking at these vectors between p and psi and z and psi, right? So let's do that. Let's look at the magnitude first. Okay. So let's over here, we want to evaluate the magnitude of h of psi. Okay? And we could go through and plug these, psi, psi is, let's see, psi is -3 plus, I used I in here instead of J. Either one is fine. I like using J most of the time though. So so psi is equal to 3 plus J4, right? Or I4. So that's what we want to evaluate psi at. We could just plug in psi equals 3 plus J4 into H, which is defined by its poles and zeros. Now, we don't have that overall scaling factor, but assuming that that's 1, we could do it. So this is our problem, but what we want to do is say, instead of doing that, instead of just plugging it in to our transfer function, we want to use this geometric interpretation using this A1 equation. So S minus Zi is this blue line, right? Psi minus Zi is the vector that goes from, or Z1, it goes from Z1 to psi. So that vector. If we wanted to know the magnitude of that vector, how would we do it? It's just the length, right? For a vector, we're just talking about the length of the vector. So what is the length of the vector from Z1 to psi? So it's going to be, so this is going to show up in the numerator, right? So we'll put this one in the numerator. So we've got, we'll just use Pythagorean theorem because that's pretty easy. All right, triangles here. So we've got square root of 2 squared plus 4 squared, right? No, because we're only going from this. So this is the vector. 2 squared plus 4 squared. So that one comes from the 0. And in the denominator, we've got the 2 pole contributions. So let's do P1 first. Square root of, this is at -3 and plus J3. So -3 to +3 in X, or in real, right? -3 to +3 is 6, right? 6 squared plus, what's the imaginary difference? 1. So plus 1 squared. Times square root of, pole 2 has the same real difference, right? Because this complex conjugate pair. So this is going to be 6 squared. But this one, in the imaginary direction, it goes from -3 up to +4, so that's 7, right? Plus 7 squared equals, so 2 squared is 4, so square root of 20 divided by square root of 37. I mean, this is going to be a mess, right? So square root of 20 divided by square root of, what did I say, 37? Divided by the square root of, what is it, 30, oh, what is it? 85. I'll just use that. So 0.0797. It makes sense that this is going to be relatively small, right? Because these are relatively long. The poles are relatively long compared to that 0 length. Relatively small, especially because we're taking the product of these two in the denominator. So that makes sense. relatively small number. So, and then we could also do the phases, and I'm not going to go through the phases in numerical detail, but we can do it sort of qualitatively. The angle of h of psi is equal to, so going back to our equation here, you add the zero lengths, and you subtract the pole, or not zero, the zero angles, and you subtract the pole angles, right? So the angles that we're talking about here are, so the zero angle is going to be this. So I'll call this, for an angle, I'll call it phi 1. Or no, we'll do theta. I like theta. Theta 1. Whatever that is, say we computed it, and it's theta 1. We would take theta 1, and we would subtract, I'll call this I'm going to go phi 1, just because for poles I'll do phis. Phi 1, and then I'll call this phi 2. So so minus the pole 1, so minus phi 1 minus phi 2. So you can compute what they are geometrically. Now, this is so, yeah, maybe back before calculators, this had some like practical use for, calculating things. But that's not why we're doing it. We're not doing it so we can like come up with like a shortcut to calculating this by hand. No, that's not. Or like we're not going to use like a ruler to measure like this is this length, this is that length, and evaluate. You could come up with an approximation pretty easily by doing that. The reason we're doing it is that we're going to learn how to figure out what gain we want our controller gain to be, to place our closed loop poles in a specific location. So that's what we're doing this for. We're going to be using this geometric idea in this chapter 5 that we're embarking upon now. So it's a geometric way of evaluating this transfer function at a given point. We don't have all of the understanding yet to know when we're going to want to do that, but this is just a mathematical tool to put in our bag that we're going to pull out in like 2 lectures. So yeah, this week we'll use it. So it's going to be super fun. But I feel like if you see these things all at once, it's like a lot. Like seeing the mathematical aspect of it. This is, I think, you can look at the equation and say the lengths of these vectors, the products and the product of them / division of them gives you the magnitude, and the differences in them gives you the phase. The differences in the angles give you the phase. That's like, I think you can understand that separately. And then when we go to do the root locus derivation, we'll just have this in our tool bag already. We don't have to learn this as we're in the middle of it, because I think that makes it really hard. So that's my opinion. Are there any questions on this this geometric interpretation? Yeah.
Yeah, for the when you're interpreting between your formula that you found for your equation one for the magnitude of HS, why are you leaving out your K value?
Yeah, so I did. I should say, assuming K equals 1. And that's just because I didn't write out the transfer function. So I just gave you the poles in 0 locations. So maybe K is something else, but it wasn't given in the problem. So I should have said that, like assuming K equals 1. So it's actually kind of interesting that you brought that up. I'm glad that you noticed that. The MATLAB function that you guys have used previously to generate simulations, you've used the state space one when you have your state space model to do your LSIM on, so A, B, C, and D matrices. We learned how to do that probably last semester, I think it was. That's one way to specify a system model in MATLAB. Another way to do it is to do the TF, which I think that we went over that as well, the TF, and then you would give it the numerator coefficients of your transfer function and the denominator coefficients of your transfer function. There's a third way that we haven't talked about, which is the ZPK function, zero pole gain function. And I'm hoping that this is the right order of the variables. I'm pretty sure that it is. You give it a list of your zeros. So you give it an array of zeros, and then you give it an array of poles, and then you give it your gain value. And so if you know your zeros and your poles, you fully define your transfer function within some constant k, which is the same k that we're talking about here. So those are three ways of specifying a system in MATLAB. Once you've defined them, so in this case, since we had the poles and zeros and not the transfer function in explicit form, I would have used this method. If you have the transfer function, you don't have the poles and zeros, you don't want to have to solve for them, so you use this one. If you have the state space model, you don't want to solve for the transfer function of the poles and zeros, use this one. All of these will give you something. They're different objects and have slightly different things you can do with them, but all of them will work to do like step, to find the step response. All of them will work to find to use LSIM to simulate. Ooh, LSIM with multiple M humps. Okay, LSIM. So you can hand any of these things to, so these SS return values, TF return values, and ZPK objects. So all these three objects will go into step just fine, will go into LSIM just fine. So whichever way you happen to have it, you don't have to even change it. MATLAB has three nice functions for putting these different forms of your system model into an object that can be used to simulate things. So pretty sweet. And we're going to be we use a lot of, in this controls section of the class, we're going to be using a lot of transfer functions. And we're going to be talking about the zeros and the poles. So sometimes you have the zeros and the poles, sometimes you have the transfer function. These two functions are really useful for specifying models in this case. And another function that we're going to get really, really comfortable with in this class is the Locus function. And this one is going to be helping you with the root locus. So that's a fun. It's not a red herring. It's a, what is that? Foreshadowing. Yes. So, what do you guys think? Should we just leave 7 minutes early? Okay. Any other questions before I shut it down?